Okay, so today we are going to talk about finally the Lorentz equations, and this is one dynamical system which is a canonical example of how chaos sets in. So we are going to study this in somewhat detail, what's going on, uh, and this is probably one of the most popular paradigms to study chaos. So I don't know whether you can see this YouTube link, but there are plenty of uh, videos on YouTube depicting the Lorentz attractor, the strange attractor, fractal attractor, indicating the sensitivity to initial conditions in chaos. In the Lorentz system. Okay, so, and for those of you who have really encountered this, this is what the Lorentz attractor looks like. This is it's a three-dimensional equations. I just write down the equations. So this is the Lorentz equations, and for particular values of these parameters R, sigma and B, this attractor, this system becomes chaotic, and we shall see that, but that's how the Lorentz attractor looks like. It really looks like wings of two butterflies, and this is of course the x, y and the z coordinate. And this particular figure also not only shows this beautiful attractor, which by the way is a fractal. It has a fractional dimension. And what this figure also shows is the sensitive dependence on initial conditions. So what's happening is that you have the blue trajectory and the red trajectory, which start somewhere they start somewhere very close to each other over here, and then what happens is that they depart from each other. So for example, you can see the blue one over here and the red one doing its own thing, and this plot marks the difference between the x coordinates of those trajectories, and you can see the difference over here. So there is an obvious difference. So the trajectories, no matter how close they start, they diverge away from each other eventually, and that's what we refer to as the sensitivity to initial conditions. And these are the fixed points of the system. indicated by these guys, and the trajectories swap around these two guys, and then again it's going to swap a few times here, then a few times here, then a few times here, a few times here, which also, by the way, is uh, has all the statistics. How many times one trajectory goes around this loop, and then this loop has all the characteristics of a random sequence. And all this wonderful behavior is happening in a deterministic system. This is an absolutely deterministic system with no stochastic element. Yet it gives you apparent randomness, and also two trajectories starting very close to each other, the red one and the blue one, they are going to depart away from each other, while at the same time the system remains bounded. So we will be able to analyze the system in much more detail. So let's get started. By the way, so the Lorentz system, this is I just write down again these equations. So these are the parameters sigma, r, and b, and we take them to be greater than 0. Are the parameters. So this simple looking dynamical system can be extremely erratic. Also, which means that the solutions oscillate irregularly. As you can see over here, there is no pattern, this is an irregular oscillation. And they eventually settle on a complicated set. The strange attractor. So the strange attractor, actually, the Lorentz attractor, this beautiful picture, this is actually a fractal in the sense that it has a fractional dimension. Unlike a fixed point which has dimension 0, fixed point is also an attractor. You know, trajectories settle on a fixed point, and it has got a dimension 0. We have limit cycles as attractors, that's dimension 1. The strange attractor is a fractal attractor, has a fraction dimension, and the dimension in this case, so the overall space is 3-dimensional. So this is an object with a fractional dimension embedded in this 3 dimensions, and one can show that the dimension of the Lorentz attractor is between 2 and 3. I think it's 2.09. We can check that, but that sort of is the idea. So before seeing, as we crank up the parameters, what happens and how does chaos set up in this equations, let's see the properties of the Lorentz system. So first obvious property of the Lorentz system is the nonlinearity. So you can see that these are the nonlinear terms. And that causes the system to be nonlinear. The second property is symmetry. If I replace xy by minus x and minus y, there is nothing that happens to the system. So therefore, if x of t, y of t and z of t is a solution, then minus x of t minus y of t z of t is also a solution. Third, this is a distributive system, and this exhibits volume contraction. And remember, we did the criteria for a distributive system. So I have a system of equations. And one way to embark is whether the system is volume contracting or not is calculating the divergence of the dynamical system. So this was one of the very first lectures, so you have to go to lecture 3 maybe for the proof of this thing, how this quantity is related to the change in volume, rate of change of volume. So let's say calculating the divergence to which is less than 0. Remember, sigma b r all were positive. So we can relate that to this gave you, remember, the exponent of the rate of shrinkage of the volume, and essentially the volume shrinks exponentially fast. Okay, so that's the idea. And what are the consequences? So what are the consequences of volume contraction? configuration is all trajectories assuming the right choice of parameters. So depending upon sigma, b and r, either the trajectories will go to a fixed point, which we'll see, or even given the right parameters. For example, over here, deriving this volume contraction or the temporal dependence of volume, we never assumed anything. So this holds for this system also. So even this attractor, essentially, finally all trajectories, if they settle on this particular attractor, and because of volume contraction, even this attractor, the volume has exponentially shrunk. So this is actually a measure zero object in 3D. By measure zero, I mean this is a measure theoretic concept, but what is, let's say you have a sphere. What is the volume of a circle inside the sphere? Well, it has a dimension less than zero, so this is a measure zero object. If I have an area, what is the measure of a line in that surface? It's a zero dimension. If I am on a line and I have a point, what's the measure of this point? Or what's the length of this point on this line? This is measure zero. So similarly, this Lorentz attractor is a measure zero attractor on embedded inside this 3D surface. So all trajectories settle on strange attractor, which is also, respects the volume contraction. It's a measure zero attractor. Measure is a generalized concept capturing length, area, volume, the measure or the metric of the space. And when I say, as I said, that what's the measure of a point on a straight line? Well, it's a measure zero object. The length of a point is zero. The area of a line is zero as compared to the area of the circle, area of the square inside it. So all trajectories settle on a strange attractor for the right choice of parameters, which is also happens to be a measure zero object. And one of the consequences is that of this volume contraction, that essentially the volume is exponentially contracting, and as t goes to infinity, the volume goes to zero. There are no quasi-periodic solutions. So why? Can you guess? So if we assume there are quasi-periodic solutions, then we are going to run into paradoxes. So, for example, let's say I had a quasi-periodic solution on a torus. So, this is not possible for a volume contracting system. Why? Because this torus is invariant. This torus is, if there are quasi-periodic solutions, this torus is invariant under the flow. So a phase space volume spread over the torus remains invariant. So I hope you understand the argument. The argument is that for a quasi-periodic solution, they lie on a torus, and that torus is invariant under the flow, but that cannot happen for a volume contracting map. So for a volume contracting map, if I have the initial volume Vt, it has to shrink down, Vt1. Finally, it has to shrink down whatever the volume is going to be. Vt is going to 0 as t goes to infinity. I start with a volume, an initial condition which is the entire volume, it is going to shrink. Now if I can start with a torus, imagine I start with the volume as a torus, and this torus represented the quasi-periodic motion, or the quasi-periodic motion was occurring on this torus. Well, this torus has to also shrink because of the volume contraction, but that means that my original assumption that my trajectory was on an invariant torus, that will be violated. So the only way to reconcile this is that I have no quasi-periodic solutions, because the invariant surface over which these quasi-periodic solutions occur, that also has to respect this volume contraction. Needless to say, that doesn't happen. Okay. So the consequence number 2 is that there are no repelling fixed points or repelling closed orbits. So that means all trajectories near the fixed points or the repellers are driven away. That's a repelling fixed point. So all trajectories near the fixed point or the repeller are driven away. But if you look at it, the repellers, that's the definition of a repeller. Repellers are incompatible with volume contraction. Okay. So what about the fourth property? So the system, Lorentz system of equation, let's talk about their fixed points. So I'll just write down the equations again. And of course, parameter. For you just plug in x0, y0, 0, 0, that's a fixed point. And for r greater than 1, there are other fixed points, two more fixed points, x star equals to y star equals to plus minus b r minus 1 and z star equals to r minus 1. So these are two fixed points. We are going to call them c plus and c minus. They occur when x is going to 0. We shall see that as r goes to 1 from above, c plus and c minus coalesce with the origin in a pitchfork bifurcation. So we shall see the bifurcation diagram of the Lorentz system soon. Let's talk about the origin. This is the Lorentz system of equations. So let's talk about the linear stability of the origin. So when I linearize about the origin, I am going to remove these nonlinear terms. So I get x dot equals to sigma y minus x, y dot equals to rx minus y, z dot equals to minus bz. So that's my linearized system of equation, and as you can see, the z coordinate has decoupled from the x and y motion, and this is an exponentially shrinking thing. So zt goes to 0 exponentially fast. And in my x and y direction, linearizing gives me I can write down here. And as I can see, the trace of this guy is minus sigma minus 1, and the determinant is sigma minus r sigma. That's the idea. So as you can see, for r less than 1, I have trace is less than 0 and my determinant is greater than 0. That means determinant is a product of the eigenvalues, so both have the same sign, and traces, so both are negative. And in fact, you can actually calculate the eigenvalues. I have not shown that calculation. So if you calculate the eigenvalues, let's say lambda, sigma, r minus 1 minus lambda, solving this sigma minus lambda minus 1 minus lambda minus r sigma, and if you solve these eigenvalues for lambda, solve for lambda quadratic equation, you can can you show that the roots are going to be real? So we are dealing with real quantities, uh, real quantities. So both roots are real. So given that this condition implies that both eigenvalues are negative, so you have a stable fixed point. So it's attracting in the x direction, attracting in the y direction, and z we already showed it was attracting in the z direction. However, for r greater than 1, you have a trace is still less than 0, but the determinant becomes less than 0. So now the eigenvalues have opposite signs. So one is positive and the other is negative, and hence I have a saddle with two attracting directions. One is the z direction and one is this attracting direction, and I have one direction which is actually repelling. So this is a saddle. So the point at the origin changes its stability as r goes from below 1 to above 1. So I can say saddle with two directions coming in and one direction outward. For r less than 1, all directions are incoming and the origin is a sink. Okay, so yeah, so this was property number 5. Now global stability of the origin. For r less than 1. So the origin is globally stable. That means for r less than 1, all trajectories come to the origin. As t goes to infinity. So how do we show that? So the proof involves something which we have not done, but essentially the idea is that define a volume which is so this is an ellipsoid, and if I in case of v dot is less than 0, so therefore v, the volume reduces as one goes forward in time for all trajectories. So essentially I have this surface, so I have Z, Y, X, and I have this spherical volume, ellipsoid volume, V, and I have defined V in this particular way, and I can show that, let's just do it. So if I calculate V dot, that would come out to be 1 over sigma, actually let me take 1 over 2, V dot 1 over sigma x dot plus, just differentiating it, y dot plus z dot, and plugging in the values of x dot, y dot, z dot from the Lorentz map, this set of equations, I'll get this guy, and that will be and when I complete the square for the first two terms, I get so for r less than 1, this guy is strictly negative, and of course x yz not the origin. So what does that mean? That means all trajectories simply keeps moving to lower B. All trajectories under the flow keep moving to a lower B. So, and this was a very generic function of xyz. So any trajectory starting anywhere would be part of some ellipsoid, and under the floor it would be keeping moving towards lower B, eventually getting attracted to the origin. So that's the idea, that for r less than 0, this is origin is globally stable. Finally, the seventh property greater than 1, as we already saw, we have two new fixed points, as we discussed, C plus and C minus, and they are, it can be shown linearly stable for r greater than 1 but less than a value RH, which was sigma plus b plus 3 divided by sigma minus b minus 1. Of course, we are assuming sigma minus b minus 1 greater than 0. Okay, so we'll come to this later, but just to give you an idea what is actually happening in the bifurcation diagram. So I have x, I have the parameter r. So I have the origin which was stable till r equals to 1. For r greater than 1, the origin loses its stability, and I have a pitchfork bifurcation where I have C plus and C minus arise. And then I have a, remember we did in this lecture, I have a subcritical hop bifurcation. Go back to your previous lecture for this sort of bifurcation diagram. And these are unstable cycles. And beyond them is a very interesting gleam of our strange attractor. So what happens to the system beyond RH, we are going to study in the next lecture. But this is an idea of what's happening systematically to this sort of equations. We started analyzing fixed points, the stability of the fixed points, how it becomes a saddle, and then two new fixed points arise, they are stable, and then how they lose their stability. And now beyond RH, what is a stable attractor in town? That we are going to see. And this is a subcritical Hawk bifurcation happening over here. So let's take this all in the next chapter. Thank you.